Hi everyone, I'm Math Rainbow Man. In this video, we discuss how we can change a rectangle into a square with the same area. This video consists of 3 parts. In the first part, we introduce the method. In the second part, we explain why the method works. In the third part, we discuss some interesting background information of the method. The method is actually very simple. Let's take this rectangle as an example. First, we stand it up. The longer side becomes vertical and the shorter side becomes horizontal. Let's put it here. Second, we form a semicircle with the diameter equal to the length of the longer side of the rectangle. Before we go on, we have to clarify the term semicircle. It refers to the edge only. It is a curve. The distance between every point on the semicircle and the center is the same. We put the semicircle on top of the rectangle horizontally in such a way that the right end of the semicircle meets the top right corner of the rectangle. This longer side of the rectangle meets the semicircle at this point. Third, we extend this longer side so that it also meets the semicircle. It meets the semicircle at this point. Let's connect these 2 points by a line segment. This line segment is a side of the square with the same area of the rectangle. Let's do some measurements. The shorter side of the rectangle is 8 cm long, the longer side is 20 cm long, and the side of the square is 12.6 cm long. The area of the rectangle is 8 times 20 cm square. It is 160 cm square. The area of the square is 12.6 times 12.6 cm square. It is 158.76 cm square. It is approximately 159 cm square. The 2 values are very close. The small difference is mainly due to the measurement error. Theoretically, the 2 areas are exactly the same. We will explain it in the second part of this video. Before we move on, let's focus on an interesting aspect of this method. Actually, we can use the method to work out the square root of a number geometrically. For example, if we want to take square root of 20, we form a rectangle with its shortest side 1 cm long and its longest side 20 cm long, like this one. 1 cm, 20 cm. We also form a semicircle with the diameter equal to 20 cm long. We put the semicircle on top of the rectangle horizontally in the way we described previously. We extend this longer side so that it also meets the semicircle. We connect these 2 points. This line segment is a side of the square with the same area of the rectangle. The area of this rectangle is 20 cm square. The area of this square is also 20 cm square. The length of this side is therefore square root 20. This side is measured as 4.5 cm. Therefore, square root 20 is approximately 4.5. Although this method is very interesting, it may not be very useful because the value obtained by measurement is not very accurate. In the coming series of videos, we are going to discuss how we can work out the square root of a number without using a calculator, and we can make the result as accurate as we want. Let's go to the second part of this video to understand why this method works. Let's first investigate the size of this angle. It is formed by connecting a point on the semicircle to the 2 ends of the diameter with the size of the angle be changed if the point P moves along the semicircle to a position that is closer to the point B? To answer this question, let's connect the point P to the center O by a line segment. The angle being investigated is now divided into two smaller angles. Let the two smaller angles be alpha and beta respectively. Alpha and beta are Greek letters. Mathematicians like using a Greek letter to represent the size of an angle. Let's see if we can work out the sum of these two angles. Notice that we are not aiming at finding out what alpha is or what beta is. We are aiming at finding out what alpha plus beta is. Therefore, we wish that at the end of some working steps, we could write alpha plus beta equals a particular value. Look at this triangle. OA is the radius. OP is also the radius. Therefore, OA and OP are equal in length. This triangle is an isosceles triangle. It is symmetrical in this axis, as this angle is alpha. This angle is also alpha. Look at this triangle with similar argument. OB and OP are equal in length. This triangle is also an isosceles triangle. It is symmetrical in this axis, as this angle is beta. This angle is also beta. Look at this big triangle. This angle is alpha. This angle is beta. As a matter of fact, the sum of all the three interior angles of a triangle is 180 degrees. This is an interior angle. This is also an interior angle. This is the last interior angle. The sum of them is 180 degrees. Taking out the things from the pair of brackets, we have alpha plus beta. Alpha plus alpha is 2 alpha. Beta plus beta is 2 beta. To bring it down to alpha plus beta, we multiply both sides by 1/2. One over 2 times 180 degrees means half of 180 degrees. It is 90 degrees. 1 over 2 times 2 is 1. 1 times alpha is alpha. 1 over 2 times 2 is 1. 1 times beta is beta. Finally, we have worked out alpha plus beta. It is 90 degrees. As a result, angle APB is found to be 90 degrees. Notice that we have worked out the value of alpha plus beta without knowing what alpha is or what beta is. This is an interesting aspect of mathematics. Also notice that if the point P moves closer to the point B, alpha will become smaller. However, the sum of alpha and beta remains the same because we can still form two isosceles triangles and we can work out alpha plus beta step by step in the same way. The objective of this part of the video is the explanation on why the area of this rectangle equals the area of this square formed by the method described in the first part of the video. Let the length of the longest side of the rectangle be C, the length of the shortest side be X, and the length of a side of the square be A. The area of this rectangle is C times X, and the area of this square is A times A. Therefore, we aim at explaining why C times X equals A times A. We wish that at the end of some working steps, we could write C times X equals A times A. Let's look at triangle APB. As P is a point on the semicircle and P is connected to the two ends of the diameter, according to our previous discussion, angle APB is 90 degrees. An angle of 90 degrees is also called a right angle. We can use this symbol to represent a right angle. A triangle with a right angle is called a right-angled triangle. Therefore, triangle APB is a right-angled triangle. In this right-angled triangle, the length of PB is A, the length of AB is C, and angle ABP is beta. Let's have some more terminology about this right-angled triangle. We need two sides to form a right angle. The remaining side in the triangle is called the hypotenuse. This is the hypotenuse. You may guess that the hypotenuse is the longest side in a right-angled triangle. We can show with clear steps that it is. The side of this angle is beta. Let's focus on the two sides forming the right angle again. Of the two sides, one is closer to beta and the other is not. The side that is closer to beta is called the adjacent side of beta. Lastly, we need to know the term the cosine value of an angle. It is found by dividing the length of the adjacent side of the angle by the length of the hypotenuse. There are 2 points to note. First, if the angle is fixed, the cosine value of the angle is also fixed. For example, in this diagram, we first measure the length of the adjacent side and the length of the hypotenuse. Then we divide the length of the adjacent side by the length of the hypotenuse, and we will know the cosine value of this 60-degree angle. Look at this larger right-angled triangle. It is formed by enlarging this smaller right-angled triangle in such a way that both the adjacent side and the hypotenuse are 3 times as large as the originals. The cosine value of this 60-degree angle in this larger right-angled triangle is unchanged because the scaling factor 3 in both the adjacent side and the hypotenuse is cancelled out when the division is performed. Second, we should focus on the value of the division instead of the terminology because the value tells clearly the relation between the adjacent side and the hypotenuse. Think of it this way. If we know the value of the division and we know the length of one of the two sides, we will know the length of the other side. Look at this right-angled triangle. The value of the division is 0.5. What does it mean? It means that if the adjacent side is 5 cm long, the hypotenuse has to be 10 cm long. If the adjacent side is 8 cm long, the hypotenuse has to be 16 cm long. If the hypotenuse is 600 cm long, the adjacent side has to be 300 cm long. If the hypotenuse is 2 meters long, the adjacent side has to be 1 meter long. You can see how useful the value of the division is. However useful it is, there is limitation. It only works when the angle is 60 degrees. For example, when the angle is 55 degrees, the value of the division is no longer 0.5. It becomes approximately 0.5736. When I was a student long time ago, I was given a book in which there were many numbers. On one of the pages, there were different values for the division of this kind. They were cosine values of different angles. After such long discussion, some of you may forget what division we are talking about. It is the length of the adjacent side divided by the length of the hypotenuse. The value of the division is very useful, and it can be found by a scientific calculator. For example, if we want to know the value of the division when the angle is 60 degrees, we press the button on the calculator with the letters COS, and the calculator will show. Then we key in 60 and the close bracket button. We press the execute button. A value of 0.5 is given. It is very convenient. Let's see if we can use the cosine value of an angle to work out the explanation on why the area of the rectangle equals the area of the square. Look at this big right-angled triangle. These two sides form the right angle. This side is closer to beta. It is the adjacent side of beta. Its length is A. This side is the hypotenuse. Its length is C. In triangle APB, the cosine value of beta is the length of the adjacent side, that is A, divided by the length of the hypotenuse, that is C. Therefore, it is A divided by C. Look at this rectangle. Let the ending point of this longer side be Q. This is a line extended from Q. The angle of a straight line at Q is 180 degrees. This angle is 90 degrees. Therefore, this angle is also 90 degrees. This small triangle is actually a right-angled triangle. Look at this small right-angled triangle. These two sides form the right angle. This is the remaining side in the triangle. This is the hypotenuse. Its length is A. Again, these two sides form the right angle. This side is closer to beta, and this side is not. This is the adjacent side of beta. Its length is X. In triangle PQB, the cosine value of beta is the length of the adjacent side, that is X, divided by the length of the hypotenuse, that is A. Therefore, it is X divided by A. Think of it this way. Suppose that we can measure this angle very accurately, and we use a calculator to work out the cosine value of this angle. The cosine value is a decimal, and we write the decimal on the left of this equation. We also write the same decimal on the left of the other equation. This expression equals this value. This expression equals the same value. Therefore, we understand that these two expressions must be the same. To get rid of the A at the denominator, we multiply both sides by A. This A and this A are cancelled out. We have X on the left. This A goes up to the numerator. It becomes A times A divided by C. To get rid of the c at the denominator, we multiply both sides by c. On the left, we have c times x. On the right, this c and this c are cancelled out. It becomes a times a. Finally, we have worked out the explanation. C times x is the area of the rectangle. A times a, it is the area of the square. The explanation is completed. The question that how we can change a rectangle into a square with the same area was one of the questions in an examination paper a long time ago when I was a student. The subject was not mathematics, it was technical drawing. I totally forget the method that I learned in the lessons. A few months ago, a friend of mine asked me the same question. It became one of the questions that I need to think about. Recently, I have been reading a book online. On one of the pages, I saw a diagram which helped me think of how I could solve the problem. The author of the book was not aiming at changing a rectangle into a square with the same area. Just the opposite. He was changing a square into a rectangle with the same area under some other conditions. Let me show what he did. Look at this right-angled triangle. Using this side as one of the sides of a square, he constructs the square. From the right angle vertex, he constructs a perpendicular line to the hypotenuse. The perpendicular line cuts the hypotenuse into two parts, this part and this part. The part closer to the square forms the shorter side of the rectangle, and the longer side of the rectangle is formed by the whole hypotenuse. The author then uses this triangle to argue that the area of the square equals the area of the rectangle. Personally, I call this method as half-area method because he argues that the area of this triangle is half of the area of the rectangle, and it is also half of the area of the square. With such argument, the author shows that the area of the square equals the area of the rectangle. Some of you may find it hard to observe that the area of the triangle is half of the area of the rectangle and also of the square. I may use paper cutting to change this triangle into a rectangle with a side equal to half of its height in the next video, so that you may find it easier to observe that the area of this triangle is really half of the area of the rectangle and also of the square. Look at another pair of square and rectangle. The author uses this side of the triangle as the side of a square to form the square. He uses another part of the hypotenuse to form the shorter side of the rectangle, and the longer side of the rectangle is formed by the whole hypotenuse. Likewise, he uses this triangle to show that the area of the square equals the area of the rectangle. Geometrically, the sum of the area of these two squares equals the area of the largest square formed at the hypotenuse. Can we express this fact algebraically? Let the length of this side be a, the length of this side be b, the length of this part be x, the length of this part be y, and the length of the whole hypotenuse be c. The sum of the area of these two squares can be expressed algebraically as a squared plus b squared. As a squared is the area of this square and it equals the area of this rectangle, it becomes c times x. As b squared is the area of this square and it equals the area of this rectangle, it becomes c times y. The second line becomes c times x plus c times y. As c is the common factor of these two terms, we can do factorization, and the third line becomes c times open bracket x plus y close bracket. X plus y is c, so the fourth line becomes c times c. Finally, the fifth line becomes c squared. Generally, for any right-angled triangle, the square of the length of the hypotenuse equals the sum of the squares of the two sides forming the right angle. Using this right-angled triangle, we have c squared equals a squared plus b squared. This is the famous Pythagorean Theorem, and it is the proposition 47 in the electronic book that I have been reading. The name of the book is The Elements of Euclid. The author is Euclid. The book was written about 2,300 years ago. Euclid changes a square into a rectangle with the same area, and I use his diagram to think of a way of changing a rectangle back into a square with the same area. This book caught my attention because of an article which describes the influence of this book on Western science and mathematics. It also mentions that this book was introduced into China by a missionary in the year 1607. A Chinese government official worked with him to translate the first 6 chapters of the book into Chinese. The Chinese government official said that everyone in the world should read the book because learning the things in the book helps a person develop a good character. The saying that learning the things in a book about mathematics helps develop a person's character is actually very innovative. In my opinion, learning mathematics from a good book helps people understand things more easily. This makes people more confident. The process of understanding mathematics arguments also helps a person think clearly. Therefore, I recommend the book to you. Thank you for watching this video.